Welcome, Professor.
Thank you, Sophie, and thank you all for coming tonight. So, in my second lecture, I will be talking about the geometry of the brain. In my first lecture, we studied the relationship between size and intelligence. It's an example of what is called a neural correlate, a correlation between a particular structure that we can see, a physical structure, in this case the size, and the function of the brain, in that case intelligence. And we're trying to find correlation between certain characteristics of the brain and its function. So tonight we'll see what we can learn from the geometry. Here I brought a brain, well, it's a 3D print of a brain. It's a beautiful structure, and what I want to know is how these patterns that are called convolution, and we'll talk plenty about convolution, play a role in the way the brain functions, but also why and how do they appear in the first place? What's the mechanism that create them, and why are they? Why it's such a complicated structure that's quite unique in nature? It looks a little bit like a dry walnut, but apart from that, it's a fascinating geometry, and this is what we will study tonight. So, quick recap. In the first lecture, we learned that Carl Friedrich Gauss, one of the greatest mathematicians of all time, had a brain that was obviously very good, but not particularly large. And the scientist in charge, Rudolf Wagner, must have been quite a little bit desperate to find something positive to say about his brain. He was given the brain of the greatest mathematician of all time, and he couldn't find any neural correlate that would indicate superior intelligence. And so he writes at the end, he says, well, the cerebrum is remarkable for the great complexity of the convolution that we see around here. And time again, we see that in the description of the brain of other great minds. Here is my favorite mathematician, Sofia Kovalevskaya, who died in 1850, tragically at the age of 41. And 2 days later, in the Stockholm newspaper, she was a celebrity, the first woman professor of mathematics. Part of her autopsy report is published, in which we learn that the brain was rich in convolution. Augustus de Morgan died at the age of 64 in London, 1871. He was the first professor of mathematics at the University of London and introduced the term of mathematical induction. And after his death, we learn from an autopsy report that the convolutions are voluminous, but for poor Augustus, not quite so intricate as that of Gauss, of course. In 1907, Mendeleev died at the age of 72, inventor of the table of elements and so on. And we learned that the brain has a luxurious presentation of convolution. Oh, nice. And of Beethoven, who died in 1827, at the age of 56, we also learn about his convolution. He had 3 doctors looking at his brain after his death. But unfortunately, Beethoven was an alcoholic, and probably his brain was on the small side because of the atrophy related to his condition. But they found that the convolution appeared twice as numerous as in ordinary brain. Of course, we can look back and say, well, that was a century ago. Of course, they tried to say something nice, some nice flourish. But let's look at ourselves and the brain of Einstein, died in 1955. There's a whole tragic comedy of what happened to the brain of Einstein after his death, and books have been written about it that I was reading. But eventually, people look at his brain, and 2013, just 11 years ago, we learned that the visual cortex is relatively convoluted in both hemispheres compared with normal brain. I'm sure Einstein would have appreciated the special relativity of his brain, but it's a very strange comment. I mean, of course, if you are a pathologist and you're given the brain of somebody that important, you have to find something important. It's like your best friend is presenting you the newborn baby, and you look at that, and obviously they're waiting for nice comment. You say, "Whoa, this baby has beautiful eyes," you know. Of course. So, of course, they were in a situation where they have to say something nice about it. But the question remains, as a scientist, if we want to talk about the geometry of convolution, how do we go about? If I look at a brain like that, what are the measures that I need to use to characterize it or to compare it to other brain, or for that matter, to other shapes. What do I do? There is a whole field about the statistics of shape. It's quite complicated to attach numbers, meaningful numbers, to a shape in space. It's easy to represent it by the point on the surface and all that, but extracting meaningful value that characterize the shape, it's quite difficult. And we are in that position for the brain. So what we're going to try is what are the measures to compare brain and to study brain. But before we do so, we're going to take a small detour to ancient Egypt and look at one of the first papyrus, medical papyrus, called the Edwin Smith papyrus. Edwin Smith was an archaeologist, an Egyptologist who bought this papyrus in the 19th century. And the Edwin Smith papyrus is one of the very first medical texts that we have. There is another one that you can find at the Antiquarian Museum, not very far from here. But this one is particularly interesting. It's about 5 meters long, and it has 48 different cases, very well explained, the way the patient presents itself and what you should do about it. And among these 48 cases, there is case number 6, which is particularly interesting for us. It's instruction for gapping wound in the skull. You see, these were like medical field text for people, medics helping the army and the soldier and all that. So there is a description of a gapping wound in the skull. So let's zoom on that. It's not very quite clear, but let's look at case 6. In black, it's written in hieratic, which is a cursive form of hieroglyphs, quite hard. The red part are notes, or footnote if you want, comments about the whole thing. So hieratics is not the one you use to, the kind of Egyptian symbol you used to see on temples and all that, the hieroglyphics. But there is a one-to-one translation between the two that is known by Egyptologists since about the middle of the 19th century. And here is the translation, first translation. It's actually written from right to left. Very interested, famous Egyptologist, Breasted, studied the manuscript in detail and a complete translation, and he found something interesting. Here, the word brain. The brain, and I flip it for you so you can read it from left to right. You can write Egyptian either from left to right or right to left, and sometimes both. So I put it for you, I flip it for you so that you can read it more easily. And Breasted writes that the brain is extraordinary interest, is the earliest reference of the brain anywhere in human records. It's not only interesting because not only the word appears for the first time, known from the context of what happens and all that, skull and all that, but also a description of what the brain looks like. And what does the brain look like? Well, we see here that the brain looks wrinkled or convoluted, like the corrugation on molten copper. That's from the original text. That's how it's described to the brain. So I don't know if any of you have seen what molten copper looks like. Personally, I don't know. But I guess it looks a little bit like a brain. Right? So that's our best description. So here is the topic of today, brain wrinkling. This is what we're going to learn. But in order to do that, we have to look a little bit better, a little bit more about the brain geometry itself. Now, if I take a slice, a coronal slice of the brain, like you see, the blue slice, and I look at it, what I see are two very distinct regions that are usually called gray matter and white matter. The gray matter around mostly the cortical area, the cortex, is that layer outside. Very important. This is where all the processing of information, sensation, higher cognition function take place. So this is where the action takes place. The white area is white because it's mostly myelinated bundles of axon. Think of them as big cables connecting different parts of the brain, transmitting information that different parts of the brain needs in order to operate and perform its task. In there, what you see in the form of the cortical area, you see this valley, which are called sulci, one sulcus many sulci, or the grooves that are gyri, and that's why we see the brain is gyrified, meaning it has a lot of convolution. So let's see when it first appears. So if you look at the development of a baby, around 5 months, you see the brain is still smooth. 6 months, all still smooth. But sometime between 6 months and 7 months, you have the first fold appearing. It's something that happened at that stage where the brain, instead of just growing like a ball, like a sphere, starts folding on itself. And that folding continues 8 months and 9 months. And even during childhood, you have a little bit more of this progression of folding happening. Now, this is a very nice drawing, but we have much better. We have scans, we have MRI scans at different periods, and we can pinpoint exactly when the first fold appears, and that's around 26, 27 weeks. And at that time, something very interesting happens, which is that if you look at the area of the brain, the cerebral area, so if I unfold these, the cerebral area grows much faster than the volume. So the volume expands, but the cerebral area increases much faster. And this is rather surprising, because this is not what you naturally expect. By that I mean, if I just look at a sphere, the volume increases like the cube of the radius, but the area only increases like the square of the radius. It's r squared by dimension. So there is always a point, if you look at evolution of a sphere, with whatever unit you use, the volume is always going to be growing faster than the area. It's completely different from the brain. So at birth, or for an adult, this is the outside area that you see. This is the exposed one. If I look, it's about 800 square centimeters here. But what you don't see, the dark side of the brain, is the total area, the folded area. And functionally, it makes sense, right? Because I told you that all the processing units actually take place essentially on the area, in that nice little layer in the cortical area. So if evolution or nature wants to pack more cognitive power, which seems like what humans have done through evolution, not as a choice, but as evolutionary pressure, if you want to put more processing unit, you have to increase that cortical area. But you can only increase so far the volume, because the skull will limit it, and the skull is limited by the size of the birth canal in humans. You cannot grow, you can not have 2 big heads for humans. We are limited that. So the solution is to increase this area where all the processing takes place by folding it on itself and increasing without increasing the volume. And so that makes quite good sense biologically, but it has also the advantage of creating different regions within the brain, modules, regions of interest that are very specific. In particular, it's known for instance, there are multiple ways of doing it, but Corbin and Brodmann in 1908 identified 52 different regions, and he believed at the time that each of these regions serves a unique functional purpose. So not only it allows you more processing power, it allows also to localize certain type of function that you have within the brain. Now, we know it's a little bit more complicated, but the big picture of localization of function is still very true. So if we want to go further, we need a brain, but we know there are plenty of brain. And that brings me to the scientist of the day, which is Professor Ellen Kuhl. So she's a good friend of mine, a long-time collaborator. Ellen graduated in 2000 with a PhD from Stuttgart in civil and mechanical engineering. She did a postdoc later in Germany. Until 2007, she joined Stanford University, and she was the chair of the mechanical engineering department, and she's now the director of a very big multidisciplinary institute, BioX, also at Stanford. Her area of expertise is living matter physics, and she started the Living Heart project that complements drug study with actual simulation of the whole heart and it's being currently used by the FDA, for instance, to streamline drug for the heart. She's written hundreds of scientific papers, won multiple prestigious prizes, and is a leading figure of biomechanics and bioengineering in the world. But as it's not enough, Ellen is also an all-American triathlete, a marathon runner, and she also competes in the Ironman. So you will meet Ellen's work, or joint work, and Ellen's work on the next slide. But actually, you've already met Ellen, because this is her brain. And I brought the travel version here, so you can pass it along, so you'll have a better idea of what Ellen brains look like. So how did I get Ellen's brain? Well, I put Ellen a few years ago in an MRI scan at Stanford with a friend Mehmet Turk, who is now professor at the University of Washington in Seattle. And we scanned her brain, and then we took all the information. And it's also on the cover of the journal I started a few years ago with Antoine Jerusalem in Oxford, Brain Multiphysics, to try to answer this type of problems on understanding geometry of the brain. So how does it work? Well, the first part is data acquisition. If you've been in an MRI scan, you know what I'm talking about. You slide in the scan, and you hear the machine go bzz, 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 and it takes all this slide picture. So these are just black and white pixels. There is fascinating mathematics about how it takes place, and big progress in acquisition and the time it takes due to recent progress of the last 20 years in algorithmics and mathematics for that. But that's another story. Once you have that data, what you need to do is transform that black and white pixel into three-dimensional information. And this part is called data segmentation. And when you do data segmentation, you obtain the three-dimensional mesh, but also which part belongs to what part of the brain, the cerebellum, the skull, the cortical area, the white matter, and so on. And you can put that together in a three-dimensional model. In green, you see the cerebellum, the little brain in the back of your head. And in white there, you see the white matter. And then this is the gray matter, the cortical area, and the skull. And we've used a scan not only to put on cover, but for multiple studies over the years. So now that we have a brain, how do we actually measure geometrical feature of the brain? So question now is to measure this wrinkle. The first idea that's been going on for a long time in neuroscience is it's quite simple but very efficient. It's called the gyrification index. And the idea is that if I take a slice of the brain, you can compute two different lengths. The first one is a solid line where you follow every single nook and cranny, right? And the other one is the length that I would obtain by putting a string over the top. So it's the length of the outer, is the length that I would do following everything divided by the length of a line on top of it. And if you see the picture, if you see the color, is the length of the blue line divided by the length of the red line. In this case, about 1.47. So you start at 1 if it's completely smooth, and as this number increases, it describes more and more convoluted surfaces. And once you have that, you can go and use that, what's called a biomarker, trying to see if different population or different condition have different gyrification index. And here is an example of what people do. For instance, you take a number of patients, in this case 40 patients with schizophrenia, and you take a reference control population. And what you see on the x-axis at the bottom are the value of the gyrification index, exactly like I told you, for different slices, coming from the front to the back, to the occipital. You take different size of both hemispheres. And then you compare the gyrification index, the average, for the reference group, a healthy group, to the group with schizophrenia. And what you see in this study, at least, is that systematically, the healthy group at a higher gyrification index, which seems to suggest that the gyrification index is a type of biomarker for schizophrenia. The geometry of the brain allows you to distinguish between normal and a rather severe condition, of course. The full story is much more complicated. There are many different studies. This one is quite clear, and there are a lot of different aspects of it. But it's just to give you a flavor. Now, since we have the full surface in 3D, we can do a little bit better. We can look at a slightly different gyrification index, which compare the area that you have, the total cortical area, by the exposed cortical area. And that's also give you, in the same way, a number. And you can look at that number locally, not just as a number for the total one, but also locally, how much more is there that you don't see, the part that you don't see. And again, there are very interesting studies. For instance, here is a study of the gyrification for patients with autism spectrum disorder. And what it shows is that there are certain areas that shows a significant difference with normal control population. And it shows you that not only that, but these are the area we know identify a special area related to social perception, language, self-referential, and action observation. So we know that these are the networks that are actually different. It makes sense within the autism spectrum disorder. Against very different topic, but you see now how we can use the analysis of the geometry of the brain to identify this type of condition. Now I can go back to Gauss, and I can try to compute the gyrification index of Gauss. Unfortunately, we don't have a measure of the exposed area, but his son, after Rudolf Wagner's death, actually computed the full area of the brain. So that we have. We know that the total area, so open area, was about 2,200 square centimeters. So in order to get the exposed area, I had to model it and make an estimation and say, well, if I know the volume, we also have the volume, I can model the brain by an ellipsoid, in 3 dimensions, and from the volume, if I know the aspect ratio of the axis, I can obtain the exposed area, and the full details are given on the text on the Gresham website. And so I found what it is, and I computed a gyrification index for Gauss, which was about 2.67, which is normal, unfortunately. Okay, so it does not distinguish great mind. But what can we say about the animal brain? Remember that during the first lecture, we saw that size by itself was not really characteristic of the power of the human brain. So maybe gyrification is, maybe this is where intelligence and power reside. So let's look at that. So here are data from a different primate brain, going for the marmosets to the monkey, the baboon, the chimp, all the way to the human, with very nice picture from my friend Roberto Toro and Katia Oyer in Paris. And they've been studying and making these amazing studies of primates and gyrification. And what you see is that, indeed, not only the human brain is much bigger, but it's also much more gyrified. We are the red dot at the top there. So maybe gyrification is a nice way to distinguish us from other animals. You also see something interesting, and we'll come back for that. If the brain is very small, like the marmoset, it's completely smooth. And that already tells us that the appearance of folding may be related to the geometry and size of the brain. And we'll come back to that. But what about us being, in the world of gyrification, superior? Well, it's all good until you start looking more widely at other animals. And when you look, for instance, for cetacean, dolphin and whales, porpoise, well, you'll see that we're not doing so well. Here is a graph of the logarithm of gyrification, so higher up is more gyrified, against the logarithm of the body weight, bigger that we are. And in particular, if you look here, we have the porpoise, and the porpoise is smaller in size, but is more gyrified. And indeed, if you look at a slice, a coronal slice, you'll see that it's much more gyrified. So if we want to use that as a way to distinguish us, again, we'll have to realize that dolphin and porpoise are all laughing at us. So we cannot use it for intelligence, it seems. We cannot use it to distinguish us. But it has already some interesting aspect. And the first question I told you is that I also wanted to know how convolution appear in the first place. What happens there? We know that it happens somewhere between 6 and 7 months, but why does it appear? And so that's a question of brain morphogenesis. And we'll see how mathematics can help us distinguish, identify the correct mechanism for it. So there's been, over the years, many different hypotheses going back a century of how teeth are formed. The first one makes good sense. That was more than a century ago, almost a century ago, is the skull constraint. And the idea is that the brain increases in size during gestation up to the point where it starts pushing too much against the skull that does not grow as fast as the brain. And when that happens, it's forced to fall back on itself. It's kind of a good idea. But this idea was challenged by a series of experiments in the 1950s by Donald Barron at Yale University. And what they did was to look at the gestation, the delivery of sheep. They look at sheep as a model animal. And they look at hundreds of sheep. This is sheep 357. And what they would do is, what he would do, he was the sole author on the paper, what he would do was to manipulate the brain or the skull during gestation. I'm not sure this type of experiment would be allowed today because, well, you can imagine it's a little over the top on the ethics side. But they were made. I call this set of experiments the silence of the lambs. And in particular, what they did was either to remove half of the brain during gestation or part of the skull. And what he realized when he was doing that is releasing, either giving space for the brain to expand or removing the skull constraint did not change the pattern that was observed. Hence, gyrification happens despite the skull constraint, and it's not the correct explanation. A second hypothesis is called the axonal tension theory, is by Van Essen, a very influential neuroscientist from the University of Washington at St. Louis. And his idea was the following. He observed, he says, well, it seems that the places that are folded on themselves are the same place where the axons are connected. And so he thought that axons should act as big ropes connecting different parts of an expanding cortex and resisting the expansion, forcing the cortex to fall on itself. And that makes sense because this is what you see, a very good correlation between axon bundle and the formation of this fold. And so for a long time in neuroscience, and up to today, it's in many textbooks, it's considered as a valid explanation. However, in around 2010, Phil Bailey and Larry Tabor from the same university did a series of experiments on the ferret. And the reason that, well, if there is action tension, if the tension is big rope pull, then you should see it when you cut in the tissue. So in the same way, if you cook a sausage and make a small cut, you see the sausage expand all of a sudden because it wants to release the tension. So if there is tension in the tissue, if you slice it, then it should open a certain way. And what they observed was the exact opposite. The tissue at this place was in compression, and there was no tension, and certainly not sufficient axonal tension in order to create this invagination. And the problem, the way I see it, is a problem with angels. What do I mean by that? Well, Richard Feynman had his story explaining that in the Middle Age, people believed that the motion of planet was due to angel pushing. He said, it's not a problem that people think about angels. We call them force, they call them angels. We can agree on that. The problem with the theory of angel, or the explanation, is that the angel pushed the wrong way. They should be pushing in that direction. Then you have a correct theory, changing the name angel with force. So the problem is that you see a motion in the sky and you assume something is pushing. In the same way, neuroscientists saw a motion, a deformation, and they thought something must be pushing, either the skull or an axon, in order to make that happen. Hence, the angel in this theory are pushing at the place where you see the deformation. But there is another manner you can make a fold, a deformation like that. And that we come to the third assumption, which is called just the tangential growth, that says you actually do not need any of these elements in order to have this folding. All you need is for the cortex to grow much faster along the surface than in thickness, and that should be enough. And we'll go back to that. And that's also a very old idea, but it's an idea for which we can work on, because we can actually now compute and see if that happens. In this case, it would be like what we call an instability, an elastic instability. So to give you an example, so here I have it's just a ruler. So I can deform this ruler by pushing it in the middle, right? I can apply a force by pushing it in the middle, but I can also deform it just by pushing on the side. Or you say nothing is pushing, but if the ruler was growing between my two hands and I wasn't moving my hands, it would naturally create compressive force that could create an instability and a deformation, despite the fact that nothing is pushing in the middle. So there is no angel pushing here, the angel are pushing on the side. The angel is the force created by the ruler extending, growing, and pushing the two sides, and creating elastic energy in the system that is relieved by changing the shape. And we know that tangential growth occurs. There are very good studies. This is a very recent study in the most excellent journal, Brain Multiphysics. Here you see at the top row the change of growth at the critical stage that I told you about, around week 23 to 25, where you see that there is very little normal growth, change in thickness, but the red part, the block below, shows you the tangential growth, meaning the tissue, the cell, grow much faster tangentially than in thickness. So we know that it happens. And so the hypothesis of tangential growth is that the angel are actually pushing tangentially and not along the side. You do not need axons, and you don't really need angels. So that's an hypothesis, and now we can start with that and see, okay, if I have that, what is the simplest type of model I can do in order to try to understand the convolution that appear? And this is what we can do, and do interesting mathematics. What we want to do is really extract the mathematical essence of the problem. So we want to simplify enough so that we really identify the mechanism. Because obviously there is no hope of directly going and understand the fully convoluted brain folding on itself. You cannot play a piano concerto before you learn how to play scales. So you want to start small, very simple, well-controlled, where you can understand all the aspects, and then you can expand that to a bigger model. So what is the simplest model? So for instance, now if I take a slice in the superior temporal gyrus, well, the slice would look like something like that. And so rather than doing the full three-dimensional problem first, what I want to do is just study that in a very simple frame in a two-dimensional problem. And so my problem now is even more. It's a two-dimensional problem when I have essentially two fixed poles, and I have the gray matter here in yellowish growing between the two poles, attached to the white matter here in blue that resists the deformation. Okay? And so now the question is that if there is growth of the upper layer but no growth in the white matter, what would happen? Is there a critical time where there is sufficient energy in the system that is going to push the side and is going to start buckling, it's called wrinkling in mechanics, wrinkling to make this oscillation. And if it wrinkles, what can I say about the number of wrinkles by unit length? So my control parameter in which I can play mathematically, where I have the thickness and I have the growth, how much growth there is, and at some point there may be enough growth in order to change the shape. So this problem, even in the two-dimensional case, is not an easy one to do exactly from a mathematical perspective. So with my PhD student a few years ago, Hamza, we built a model, we developed a model for this very simple problem. It took us it took Hamza about a year and a half to do the model, and another couple of years to study what are the consequences of the model. Right? So there is no easy way to sugarcoat it for you. The model is not simple. I cannot just show, oh, look, it's one equation, x equals 2, and we saved. No, it took years of work, very hard work. But for once, I'm going to take you behind the curtain and show you a little bit what it looks like. And this is what Hamza models look like. It is a two nonlinear PDE for two variables. They're complicated. They're very difficult to study. There is no exact solution. It's not like you can write on a piece of paper the solution. They come with a lot of boundary conditions that take another couple of pages. Don't worry, Hamza didn't do all that by hand. We have a very nice, sophisticated way to do it. But we have a model that describes what happened to this little slab in 2 dimensions under the growth. And now we can study it. So one of the first things you can do is you can go to the computer. We have equation. Just run the equation and let's see what it looks like. This is what I did with the group of Alain Goriely in Stanford. They're very good at this method. They call finite element modeling. And here you have the yellow slab that is going to grow in that model, and it's just attached to a soft tissue below. And this is what happens when you do that. It grows, and poof, all of a sudden, you have a very quick wrinkling instability. Yeah, again. So that's good. These equations support the type of solution that we know physically should arise in this system, but you can go further. We have method, we call asymptotic method, to study this equation and really extract the interesting aspect. And what you can show is that there is a critical amount of growth after which the solution that you should see is not the flat solution, but it's the wrinkle solution. And in the simplest case, you can write it as the ratio of two elastic moduli to the power 2/3 times a coefficient. Specific form does not matter. What matters is this ratio. It describes how soft the cortical layer is compared to how soft the substrate, the white matter is. It's just a material property of the two that governs how much growth you must put in the system before it starts moving. And we know that the same type of problem arises in many physical problems. You can grow swelling gels, you can shrink. Any type of wrinkle you see, for instance, on an apple when it dries is the same type of compression that you see. All these wrinkles are more or less the same physics, not coming from growth, but coming from differential aspect, creating compression in the system, leading to this nice wrinkle that you see everywhere. But once you know the growth, you actually also know how many wrinkles there are per unit length. And it's the square root of that gamma critical divided by the thickness. Now that's very interesting because it tells you how many wrinkles you should see and how it depends on the thickness of the cortical layer. Especially, since it's 1 over the thickness, you should have more wrinkle for the same length when the cortex is thin, and less wrinkle when the cortex is thick, or relatively with 1/3. So you can go back to the brain and see how this prediction, this qualitative prediction map, and it works well. We know that when we reach a certain amount of growth, for instance, 65% versus 76 and so on, we see this fold appearing just like in the brain and growing as we predict. But more interesting, there are also pathology, very severe pathology that occurs during development. The cortical layer is not a single layer, it's multiple layers, typically 6 layers in the human brain of different type of tissue. And there are a lot of different genetic conditions, but one which is called polymicrogyria, where these layers do not establish themselves properly, and the cortex is much thinner. And polymicrogyria means a lot of small gyri. And the result is that you should have more wrinkle with thinner cortex, as we predict, and what is seen. Polymicrogyria is always associated with very thin cortex. And there is the opposite one, where you have less wrinkle when the cortex is very thick, another condition called lissencephaly, which is a smooth brain. If the cortex is sufficiently thick, then you cannot fold the brain on itself. And it also explains why very small brain do not have fold, because for a given size of thickness, you need a certain extent to be able to form one fold. And the one fold that you see, for instance, is achieved in the smallest mammal that still has folding, which is the ferret. It has very simple fold. It has just the right side to accommodate, for a given thickness, the number of fold. And so it's really thickness that controls the apparition of this fold. But now, if you do that on two slabs, we can go much further, and we can go to the full three-dimensional problem. And for instance, we study the effect of curvature, because not all brains are sphere-like, or brains is a little elongated, but not that much. But you find brain, for instance, the wombat has a very spherical brain, called brachycephalic, whereas the hyrax has a dolichocephalic brain, an elongated brain. And they're very different type of patterns. And so we thought it'd be interesting to look at the effect of patterns appearing on a curved surface rather than just on a flat slab. So the surface has large curvature, so it's very curved at the tip, and small on the side, a small curvature. And what we've shown from the study of this equation, but now put in the right geometry, is that curvature always delays the instability, meaning a place that is curved, you need more growth in order to make this wrinkle appear. But that also implies that on a surface that is curved differently at different places, the pattern that you see it is wrinkle should always appear on the flat side first. And this is also what you see. When you look, for instance, this is a simulation of that, you see the patterns appearing first on the flat side, but also aligning itself with the principal direction. And that's why the hyrax has these sulci patterns that are along the side. Now, we talk about gyrification index, we talk about the convolution and how they appear. I want to show you for last part, a very recent approach that against relate geometry to the brain. And we're really talking about things that have been happening in neuroscience and applied mathematics for this type of problem in the last 2 years or so. These are called brain eigenmodes. So let me give you a small introduction of what I mean by that. Suppose that are interested in the shape of a string. You can think of a violin string, but think of a curve that does not move in space. And it has this pattern that has very high frequency, but also very slow frequency. The way you can do it mathematically to study that is to decompose that patterns into simple pattern by looking at patterns that have one bump, two bump, all the way to as many bumps as you want, infinitely many. In this case, I have 20 different bumps. Okay, so these are just sine and cosine functions that are on a given interval, W1, W2, and so on. And the idea is that you can capture the shape of this string by finding the best way to match that string with a finite number of eigenmodes. So for instance, a very coarse scale, I would use just the first two ones, the first two modes, and I would capture the overall shape, but not the fast frequency. So that would give me an idea of the shape, a global idea of the shape, but not other aspects. Okay? If I do a fine scale, for instance, if I take 20 modes, I'll capture everything. I capture also the fine scale. So you can actually do this not only for a string, but you can do that for the full brain. And people have been, we have the power to do that on the computer and the ideas, and people have been looking at that aspect over the last couple of years. It's a very recent paper in 2024. And you can see that starting with a brain, the different eigenmode decomposition of the brain is you can have a very coarse scale, which is essentially smooth, that would give you just the overall shape of the brain. And as you add more and more mode, you sum all these mode, you start seeing the finer feature of the brain. And the idea is that there are certain aspects or function of the brain that are related to different scales of the brain. In particular, in this paper, they look at eigenmodes and early psychosis. And they look at what frequencies, because it is a spatial frequency, of the brains are relevant for this problem, for this developmental problem, a very serious one. And what they discover, so here at the decomposition, as I told you, you see the smooth one, and as you add more and more mode, you start seeing the fold more and more detailed. And what they observe is that there are certain number of modes that are highly significant, between 5 and 17 or so, where there is a significant difference with patients with early psychosis compared to a control group. Again, showing the very interesting fact is that early psychosis, and we saw autism spectrum disorder and schizophrenia, might all be related to very early on developmental problem, because this is when the shape of the brain is established. And so there is a direct link between geometry in the development and some of these conditions. So there is very clear neural correlate, even though the details are much more complicated than just a simple picture, like more wrinkle or less wrinkle. There is a whole zoo of biomarkers that you can use or you should use in order to make precise statement. But there is clearly a relation between this abnormal early development of the geometry of the brain and some of these conditions. And that's already very interesting. But also recently, in the last 2 years, what the same researchers have shown is that the brain activity itself can be also captured by the eigenmodes. So by brain activity, we'll talk about that in the next couple of lectures, I really mean the electrical activity that takes place in the brain, that's thought process and all that. Everything that we associate with cognition is related to brain activity, which is a change of electrical activity within the brain. And what they show is that you can capture brain activity by having the same decomposition, showing that geometry is also not only related to developmental condition, but it's also a good way to capture how the brain normally functions. Right? So it's very new, it's a controversial a bit, and people talk a lot about this issue, but it is a very nice and very attractive ideas relating geometry to function. Now, as the last part, we talk about geometry. As I told you, geometry, what it does, this convolution, is create different regions of the brain, very easily to identify, for example, the 52 Brodmann region. So it creates this different patch where we think that certain processes take place. But when we look at a slice, we can identify them. There are different regions of interest. Here I place a few of them that corresponds to well-defined region that you can spot. And what you see is that between this region, you have this long, thin line, this bundle of axons, a lot of different neurons, the long tail of the neurons connecting them, exchanging information left and right, right? It sends information right, it processes information, send it to other place. But not all these regions are equally connected. They're not all connected. Certain regions are connected and some others are not connected. So I can follow, in principle, this connection, and I can make lines between this connection. I can start drawing. Region 1 is connected to region 5, so I'm going to put a line in between. And I can say, forget about the brain. Let's look what's left. And what's left is a graph or a network. And now the question is, what is the information that is contained in this graph that can tell us something about the brain? And this is one of the biggest revolutions of neuroscience, is the ability to study the brain through its network. It's so important that there is a word in the Oxford English Dictionary, which is the connectome, which is the network of the brain. And that's what we'll see next time. Thank you.